Now we're going to look at tries, which is a class of combinatorial objects that really has only come into study in recent years due to computer applications. Not found in classical combinatorics, but actually are very interesting, rich combinatorial and analytic properties. So I'll spend some time really just talking about what tries are and their applications before we talk about the analysis. So one way to look at a trie is just as a binary tree where the external nodes can be marked. Black ones are called void nodes, and then the white ones are non-void. So you take a binary tree and mark some of the external nodes to be void. Now there's a rule, and that is that you can never have two void nodes that are siblings of each other in a leaf. So the sibling of a void node is not void. That's the rule. So that's what a trie is. Now that seems kind of arbitrary, but you'll see when we look at applications how these rules play a role. Actually, for an exercise, you might give a recursive definition of what a trie is. The usual way that we think of tries is as representing a set of bit strings. Each trie corresponds to a set of bit string where each non-void external node represents one bit string. And you get the bit string by taking the path from the root to a node, taking a 0 when you go left and 1 when you go right. For example, if we go 0, 0, left, left, right, right, left, we get down to that non-void external node, and we say that that node represents the bit string that we got that defines the path that we got there, 0, 0, 1, 1, 0. Or over here, 0, 0, 1, 0, I'm sorry, 1, 0, 1, 0, that non-void node represents the bit string 1, 0, 1, 0. The path from the root to a node defines the bit string. So now the void nodes have a different interpretation that derives right from this definition. For example, if we go right 4 times and then left, we come to a void node. What that means is that no string with that prefix is in the set of strings represented by this trie. The trie represents, in this case, 1, 2, 3, 4, 5, 6, 7 bit strings. And then the void nodes represent the prefixes of all the bit strings that aren't represented. So that's what we think of as a trie. It corresponds to a set of bit strings. Or another way to look at it is it's all worked out here. So this trie represents, as I said, 7 different bit strings. Those are shown at the top. Now on the left is the bit strings that from that set that start with 0. And on the right, trie on the right represent the bit strings of that set that start with 1, with the 1 stripped off. And so recursively going down, that's another way to see the sets of bit strings that are represented. Now this only works for sets of bit strings that are said to be prefix free. So that is, no member of this bit string, of this set of bit strings, is a prefix or another one in that set. We can handle that by using void and non-void internal nodes, but in applications I'm going to talk about that are typical, it's okay to just work with prefix-free sets. So, like for example, fixed length. If all the bit strings are the same length, then it's prefix-free, because they're all different. They're all the same length, and they're different. You can't have one being prefix of another. And that's a typical and useful application of tries. So this is a trie that represents those 3 strings. There's lots of applications of tries. If you look in our algorithms book, you'll find trie code for sorting, for symbol tables with string keys, and for suffix arrays, which I'll refer to in a minute. They play a role in classic data compression algorithms, Hussman's code and Lempel-Ziv-Welch compression. And we'll look at the use of tries to understand decision-making, collision resolution, leader election algorithms. They play a very important role nowadays in network systems and bioinformatics, internet search, all kinds of commercial data processing. Very important data structure that's often overlooked. That's why I'm taking the time to talk about some of these applications to motivate the analysis, because they're not so easy to analyze, as we'll see. So here's the basic application, which is for symbol tables. So trie represents a set of bit strings. So what we have is, just going from the definition, a search algorithm for determining whether a given bit string is in the set represented by the trie. And the basic idea is, if the leading bit of your key is 0, go to the left. If it's 1, go to the right, and then use the remainder of the string recursively. If you get to a void external node, it means that the one you're looking for is not in the set represented by the trie. If you get to a non-void external node and you're at the end of your bit string, then you report success. You did find the key. So for example, let's say we're going to search for the bit string 0011 in this trie. Start with a 0, go to the left. Next one's a 0, go to the left. Next one's a 1, go to the right. Next one's a 1, go to the right. We're at the end of our string and we're on a non-void external node, so that string is in the set of bit strings represented by our trie. Let's look for 10110. So start with a 1, go to the right, 0, go to the left, 1, go to the right, 1, go to the right. We hit a void external node, so that string is not in the set represented by our trie. It's a very natural search algorithm, have the trie represent a set of bit strings. Of course, everything can be represented as a bit string, so this is a natural algorithm for anything represented in a computer. Of course, we're going to want to, for an algorithm like this, want to know what's the expected search time under reasonable model of randomness. That's the type of thing that we want to analyze. Now, what about inserting new keys or a new bit string into the set represented by the trie? Well, what we'll do is we'll insert by searching until we get to a void external node. So if we wind up at a internal node or non-void external node, that means that we'll have a prefix-free violations, and we can deal with that in some way. But the insert a new key, it's going to wind up at a void external node. So to insert 01110, we go left for the 0, right for the 1, and now we're at a void external node. And so now what we want to do is, for each remaining bit in our key that we want to insert, we want to add a new internal node and with one void external child and then the other one corresponding to our bit. So in this case, our next bit is 1. So we put, if the key started 010, then it's not in the set of strings, but 011, that could be this one. Then we do it again for another 1, and then the next bit is 0, so we put the void external node to the right and non-void to the left. So that's how we would insert 01110 into this trie. Now, there are variants where you just keep track of the tail in some way with pointers, and people, and those are well studied, and there's lots of reasons to do that sort of thing. But the simplest version also is very effective, and that's what we'll stick with right now. So that's a search algorithm and an insertion algorithm that gives the basis for symbol table using the trie data structure, which is a very useful algorithm. And then natural question that probably already occurred to many of you is, what about these void external nodes? It seems kind of a waste to have all these void external nodes there in this data structure. And so we're going to want to analyze how many there are to make sure that we understand how much space a trie takes. But it's a very compact data structure, and that analysis is certainly interesting and relevant in practice. Okay, so here's another application of tries. What we want to do is we have a given string S, and just for an example, I'll use a genomic string made up of A, C's, T's, and G's. And these things could be huge. It could be billions of letters. And we want to know, is a particular substring in our string? So like if for this string, is ACCTA in there? And the answer is yes, starting at 0. What about CCT? Yeah, there's plenty of places where CCT occur in this string. What about TGA? No, there's no occurrence of TGA. So we have a specific string that's huge, and we want to be able to quickly do substring search. And there's all kinds of applications in genomics where it's important to be able to do an operation like this quickly. So search in genomic data, and this is also useful in internet search. When you do a Google search, you not only get to the page that you're looking for, but you get context. You get where the substring is in that page, and that uses a data structure like this and many other applications. So the solution method that I'll talk about is a so-called suffix multi-way try, generalizing the try for this problem. And so the idea is to if you have your given string, what we're going to do is work with all the suffixes of the string. So the original string, A, CCT, A, G, G, CCT, if we leave off the A, then we have CCTA and so forth. So if the string is of size n, we have n strings for all the suffixes. And we're going to treat those as different strings and just insert them into the try. That's called a suffix try. Now notice that's prefix free. None of these is a prefix of another because well, they're all different lengths. It's a prefix free set, and they all end. We have them all end with a character that isn't found anywhere else in the try. So then the idea is that every internal node of this try corresponds to some substring of our original string. So to answer the question, is X a substring of X, we use the characters of our query to traverse the try. So for example, if we're looking for A, C, CTA, then we can, when we get to a non-void external node, that tells us that that one is in there, and it tells us what position it is. So we built the try AC. If we see something that starts with AC, then we look starting at position 0 and continue our search, and the ACCTA is there. If we encounter a void node, then, so for example, if we're looking for CCT, then we find a void node, CCT is there because we found it in an internal node, but something like TGA, we end up at a void node and we're out of there. If we reach the end of the string, then we're fine. If we hit a void node, we know that it's not there. So this is a very simple algorithm to answer this is X a substring of S question and a fine application of tries. And again, the number of void nodes and what does it mean to be a random try and how long is the search and so forth, all of these kinds of questions are going to be important and relevant in practice. Here's another application of tries. Tries is a model for an algorithm, so-called leader election algorithm. This is important in distributed systems. So the idea is you have a group of individuals and they would need to elect a leader. And what they're going to do is each flip a coin. So it's a distributed, it could be a large number of them, they'll each flip a coin. We'll count ones as winners and zeros as losers. So everybody that gets a 1 when they flip a coin survives for the next round. And the ones that got 0 are gone. So now we just worry about the ones that got 1s. Again, they each flip a coin. In this case, the 2 green ones get a 0, so they're the losers and they're eliminated, and only the ones that got 1 continue to the next round. They each flip a coin. Again, 2 are eliminated and 3 are left, the ones that got 1s. They each flip a coin. In this case, they all get 1, so they all advance to the next round. And then we have a void node. And then again, nobody eliminated. Now they each flip a coin, and only the blue one survives, so that's the winner. So this is a very simple method for choosing a leader in a distributed manner among N people. Now there's a possible problem, and that is a procedure might fail. What if they all throw 0? Then in that case, they're all losers. There's no winner. Procedure might fail. So obviously we're going to be interested in what's the chance of failure. Well, it's the probability that the rightmost path in a random try ends in a void node. And what do I mean by a random try? Well, it turns out that the model that associates with this and also works for symbol tables is it's a try that you get by inserting infinite length random bit strings into an initially empty try. So there's 3 diverse applications of the try data structure for a symbol table, for substring search, and for distributed leader election. And all of this is to motivate studying this combinatorial structure. So for distributed leader, we want to know what's the number of rounds. Well, it's the expected length of the rightmost path in a random try. That's how many rounds, and then your probability of success from that, you can calculate how effective this method is going to be. So that's a brief description of tries, and next we'll look at analysis of try parameters.